Good afternoon, everyone. I'm Professor Andres Velendowski, Head of School of Mathematics and Physics at University of Lincoln, the school which hosts Lincoln Week of Math and Physics 2021. Welcome everyone who came to watch our lecture. Just to remind you that you can ask questions, you can post your questions at any moment of time during lecture or after lecture. And there are two channels to do that. You can do it directly in a live chat of YouTube, just over there. Or you can click a link which also appeared in a live chat right now. And it was provided in invitation email to type your question completely anonymously inside of Padlet. So both channels are fine. In the beginning of our hour, I will just say a few words introducing our school and university which hosts the event. Those who come to every single our lecture would hear these words several times already. So you will know everything by heart. However, those who come for first time, this is basically for you to have a few words about our school and university. Hello everyone, I'm Professor Andres Velendowski, Head of School of Mathematics and Physics at the University of Lincoln, which hosts Lincoln Math and Physics Week 2021. This week forms a part of British Science Week, which runs also the same dates. This year we have our events, lectures all online. Traditionally, in previous years, you would come to our public lectures to our lovely campus by the Brayford Pool, by waterfront. This is how campus looks in the evening. But today we do it online, and in my introduction, I just would like to give you a few words about our university and the school which organizes these lectures. Lincoln is a small city for approximately 100,000 inhabitants. Our university is right next to the center, just about 10 minutes walk. City itself is quite old. It was already found by Romans soon after they came to the British Isles. Once it was also base of famous Legion 9 Hispania before Legionnaires moved to York. The city received quite early in 86 prestigious status of a colonia, so it became Lindum Colonia, and Lincoln name came later on. And that already happened in times of Emperor Domitian. The place had a forum and a bath and all facilities of Roman times, and was a place for retired legionnaires. Even today, you still can find remains, Roman remains, and you can walk or drive under this Roman arch of Roman gates. The only one in Britain through which traffic is still allowed. Next big step in Lincoln development was in times of another visitors. Then William the Conqueror, William I, came to British Isles. Very soon he ordered to build a famous Lincoln Castle on the top of Lincoln Hill. And some years later, also even more famous Lincoln Cathedral started to be built just opposite to Lincoln Castle. This cathedral is considered to be one of the most beautiful buildings, if not the most beautiful cathedral in Britain, and probably around world. For some period of time, that was in fact the tallest building on the planet when a wooden spire was on the top of a main tower. Cathedral is, of course, was a seat of learning already from Middle Ages. However, university appeared in Lincoln much later, in the end of 20th century. Campus by the waterfront was opened by Her Majesty the Queen. And much later, already in 21st century, College of Science was opened, which included School of Mathematics and Physics, which opened its doors in 2014. And 3 years later, we also opened our own building, which we share with schools of engineering and School of Computer Science. And just in about months, we will be celebrating 4 years of this beautiful Isaac Newton building, named after Isaac Newton, a gentleman who also comes from Lincolnshire. And our lectures are primarily aimed at those who study mathematics or physics at A levels. Of course, they're accessible to everyone who is curious about maths and physics. But maybe those who study a maths and physics level will think about continuing their education after the school. And therefore, I'll mention what our school has here on offer regarding degrees in maths and physics. As you see, we have full range of degrees, bachelor, 3 years degree, and integrated masters, both in mathematics and in physics. We have also various combinations. For instance, combination of another Asian subject, one of most Asian subject, philosophy. So we have degree mathematics with philosophy and physics with philosophy, where philosophy is a minor component and physics or maths are a major component. And we have also combination of mathematics and computer science, and mixture of mathematics and physics as well. And with that, I welcome you to our next event in Lincoln Maths and Physics Week 2021. And I hope you will enjoy it. Welcome. Hello, everyone. Now we move to our main program, which is a lecture. And I'm very happy to be joined this afternoon by Dr. Matthew Booth. Hello, Matthew.
Hello.
So I just very briefly introduce Matthew. Matthew comes from Lincoln, so he's a Lincolnian. He got his undergraduate degree in mathematics and physics from University of Leeds in 2010, which followed with a master's in quantum technologies, also from University of Leeds. And then he continued for highest degree, a research degree, doctorate, a PhD, also University of Leeds, and it was in molecular nanoscale physics. Matthew first joined our school in 2015, first as a senior technician in physics, and in 2016 he became a lecturer in our school. And I'm very happy that Matthew joined us this afternoon, and he will tell us something about which has very enigmatic name. It's a quantum dots. Floor to you, Matthew.
Thank you very much, Andrei. So, yes, hold on. So you should see my slides now, and you see the title there is quantum dots, what, how, and why. So Right off the bat, let's change the title of the talk to Semiconductor Nanocrystals Below a Certain Size. So that's not quite as exciting sounding, but it does say a little bit more about what quantum dots are. So this is what we're going to try and explain. We're going to have to explain what a semiconductor is and why, what happens when we go below a certain size. So to start off with, we'll look at some physics. We'll talk about what a semiconductor is. And this image of a rock you see here is an example of a naturally occurring semiconductor called bornite. And you may have heard of a semiconductor called silicon, which is the foundation of our modern technologies, digital technologies. Then I'll move on to talk about what an exciton is and what a quantum dot is and why size matters. Then I'll talk a little bit about how we can make quantum dots using thermodynamics. So that I'm going to ignore a lot of chemistry here, so apologies to any chemists in the audience. And then I'll talk a little bit about once we claim to have made nanocrystals, how we can actually verify that. And the technique we would usually use is electron microscopy. So at this point, I'll show you some nice images. Then finally, I'll talk about some application of these materials. So there's applications in the emission of light. So the latest TV screen technologies are based on quantum dots. And also they're very useful for bioimaging applications. And we can also talk about applications that make use of the absorption properties of quantum dots. For example, photovoltaics. And we'll discuss a little bit about why they're better than bulk semiconductors and molecular dyes. So just before we begin properly, you may have seen quantum dots in the news about a year ago. So there's talk of what people call vaccination tattoos. So I mentioned biological applications. These materials have been kind of talked about for medical tattoos that store medical history. So we begin our story, if you like, at Doddington Hall near Lincoln, where a gentleman called Edward de Lavalle once lived. So this is a photograph. So we go every year, we take our physics students there every year. This is a photograph of our first ever physics cohort at Lincoln. And I did see Sorsha was in the chat, so maybe she can say hello. She's right in the middle there. And this is Edward de Lavalle. So he's not very famous nowadays, but he was quite famous in his day. He was a contemporary of Benjamin Franklin, and he's credited by some people with the invention of the lightning rod. But the reason we're talking about him today is because of this work he did. So this is called an experimental inquiry into the cause of the changes of colours in opaque and coloured bodies, and then another set of words. So very long titles in those days. And if you look at this portrait, you'll see in the bottom right-hand corner there, he's included his coloured glasses in his portrait. So he's kind of showing off a little bit the social media of his time. So just to say, we have open days, and at least in the autumn, if you come and visit Lincoln, you will see some coloured glass. The cathedral, if you go up the hill and look. And just to say a little bit about how this coloured glass was formed, they would add different chemical compounds to different parts of the glass to produce these different colours. So you might ask, why am I talking about coloured glass? And the reason is because quantum dots were discovered by looking at coloured glass. Okay, so I don't expect you to read all this, but this is the paper kind of credited with this discovery about 40 years ago, and I'll draw your attention to some sentences. So down at the bottom here, we have quantum dots as a new class of objects that exhibit size effects. So they're three-dimensional microscopic crystals, so this is nanocrystals, of semiconducting compounds grown in a transparent dielectric matrix. So in other words, grown in glass, right? So we're looking at coloured glass. And to explain this plot on the right-hand side there, this is on the horizontal, it's kind of size of crystal is decreasing to the right. So on the right-hand side, that's small crystals. On the left-hand side, that's big crystals. And the vertical axis there is energy. So this is effectively the colour of light emitted by the crystals. And we see that, when we're down at this very small range. So the units here are angstroms. So on the right, it's about 2 nanometers. On the left, it's about 10 nanometers. So we're really at the nanoscale here. And we see this size dependence of the color. Okay, so this is this quantum size effect. The color that a crystal is depends on its size when we're down at this small scale. So they did this work with copper chloride, which is certainly not an exotic material. Okay, so this really is a property that comes from this size effect, not really from the material itself. So you could maybe get this pale yellow colored glass if you just added big copper chloride crystals or made glass from a copper chloride solution, you would get this color. But if we make crystals from the copper chloride and really control the size, we can get many different colors from the same compound. We don't have to use different compounds. So we see the two keywords here. We have semiconductor at the top there. We have exciton in the figure caption. So these are the two words we really need to explain before we can understand this quantum size effect. Okay, so what is a semiconductor? So the brief definition is that it's a material with electrical conductivity intermediate between insulators and conductors. So conductors conduct electricity and insulators don't. Okay, that's quite vague, and we're going to explain that in more detail. But first, let's look at some of the materials that have this property. So we've mentioned silicon. There's germanium as well. These are kind of naturally occurring single element semiconductors, but we can combine different elements. So we can take one element from the left of silicon, one from the right, put them together and also get a semiconductor. And we can keep going, we can do that. Again, the pattern breaks down a little bit with lead there, but you see how this works. So if you wanted to understand this, you would maybe have to do chemistry or physics at university. We won't really talk about this too much today. But the point is, there's many, many materials that have this property of being a semiconductor. And what I'm particularly interested in is copper indium sulfide. It's a ternary semiconductor, so it's made up of 3 elements. And this allows us to kind of vary the composition quite easily as well as the size. So I'll mention that again later. So to really understand this, we have this vague definition, a material with conductivity. It's not a conductor, it's not an insulator, it's somehow in between. Okay, so in order to kind of understand that more deeply, we need to look at the electronic structure of atoms and solids. So a single atom looks like the diagram on the left. So just to say, the only thing we're really interested in here is the vertical axis, this energy axis. We're going to talk about the energy of electrons in a material. The horizontal kind of axis there doesn't really mean anything. It's there just for purposes of illustration. So electrons in an atom exist in these discrete energy levels called atomic orbitals. So they're those horizontal lines. If we combine many atoms into a crystal, okay, even though the individual atoms are identical and they have the exact same energy levels, when we force these atoms together into a crystal, all these energy levels cannot exist at the same energy. They have to kind of separate ever so slightly out. So you see this kind of group of very closely spaced energy levels. So say if I think there's 11 atoms here in this crystal. So in each of these bands, as we call them, there would be 11 energy levels. And as we keep adding atoms to our crystal, if we grow our crystal bigger and bigger, then these kind of energy levels in these bands are so close together we can treat it as an effectively continuous band. And these bands are separated by band gaps. Okay, so we see these rectangles, which are these bands where electrons can exist. This range of energies that the electrons can exist at. And in between these rectangles, there's kind of forbidden energies. Electrons cannot have this energy. So this is really using quantum mechanics here. So if we start adding electrons to our system, so we add electrons at the lowest possible state first. So on the left there, we've added an electron, which is represented by a blue circle, into the lowest energy level, so the lowest atomic orbital of the atom. When we have n atoms in a crystal, we then get n electrons in that band from those n individual atoms. And we keep filling up like so. Okay, so you'll hopefully see how this works. Every time we add an electron to a single atom, we get n electrons in a band. Okay, so these electrons down at the bottom here, these are very, they're low energy, they're very tightly bound to the nucleus. These atoms these electrons, in the middle band, they're more loosely bound to the nucleus, so they can be quite easily removed. And if we had electrons in this upper band, they would have enough energy to freely move around the material. So they would become delocalized from a specific atom. And these are the electrons, once they're in this top band, that would conduct electricity. Okay, so if we want to conduct electricity, we want electrons in that top band. So now we have this kind of simple picture of the electronic structure, we can discuss conductors and insulators. So in a conductor, these bands actually meet. There is no band gap. Okay, so what this means is we only need to input a very, very small amount of energy to excite an electron. Okay, so this electron has been given an extra amount of energy from some external source, and it's very easily made its way into this upper band, right, where it can move around the material, which we know as electricity. In an insulator, however, there is a large band gap. So there's a big gap between these bands. So there's this full band down at the bottom and this empty band at the top. And in order to excite an electron from this lower band into this upper band, we have to put in quite a large amount of energy. So typically, if this gap between these two bands is more than 4 electron volts, don't worry about those units, it's just a unit of energy, then we can achieve this conduction. So a semiconductor is in between these. So what that means is it's an insulator that has a very small band gap, so less than 4 electron volts. And this value is significant because this is the optical region of the spectrum. Okay, so this band gap energy, this energy that separates this full band and this empty band, this corresponds to wavelengths of light in the visible spectrum, in the UV and the near-infrared, either side of the visible spectrum as well. So we need a relatively small amount of energy to excite an electron into this band such that it can conduct electricity. So it's all about the separation between these bands. So now we can talk about what happens when we input energy in the form of light. Okay, so just to say some terminology, actually, this full band down at the bottom with lots of electrons in, this is called the valence band, and this empty band at the top where there are no electrons, this is called the conduction band. So again, just to kind of remind you, the only thing we're interested in is the vertical position of these electrons. The horizontal position doesn't really mean anything. So imagine we shine some light on this system. Okay, we're going to talk about light photons. You can think of these as particles of light. So if the particle of light that is coming in has energy bigger than this band gap, then it can be absorbed by an electron, and that electron will be, we say, it would be promoted into the conduction band. So it's been given enough energy such that it can move around the material. Okay, but that energy that it's been given has to be bigger than this band gap. So very, very quickly, this drops back down right to this, the edge of this conduction band. Okay, so that happens, on the picosecond timescale, and this energy is lost in the form of heat, basically, vibrations of the crystal. But once it's at this band edge, eventually it will drop back down into this valence band, this full band at the bottom, and that energy that it's lost from going from the conduction band back down to the valence band is emitted in the form of a light photon. And that emitted light photon will have energy equal to this band gap. Okay, so the color of the emitted light depends on this energy between the valence band and the conduction band, which is called the band gap. Okay, so that's what a semiconductor is. It's a material that has a valence band and a conduction band separated by an energy, so that we have like a threshold energy that we have to put in before we can achieve conductive effects. Okay, so next we need to talk about what an exciton is. So this is kind of the key thing in order to explain quantum dots. So let's look again what happens when light is absorbed. So we have this incident photon with lots of energy. Okay, it excites an electron into this conduction band. And if we look down at this conduction band, we see that there's a vacancy where the electron used to be. Okay, there's a gap, and we call this a hole. And from the perspective of this hole, okay, it's surrounded by negative charge. So we can instead model this mathematically as a positively charged particle, okay, with its own mass. So we can treat, it's kind of a neat mathematical trick, we can treat this absence of a negatively charged particle as the presence of a positively charged particle. Okay, we can actually really treat it as a particle. Okay, so we have this particle in this conduction band, which is negatively charged, that's the electron, and we have this positively charged hole in the valence band. So what might happen when we have this negative and positive hole, negative electron and positive hole? Well, they are attracted. So opposites attract, right? We have a negative particle and a positive particle. So these will feel an attractive force between them. Okay, and they form what we call a bound pair. And we can think of this as a particle in its own right. And we call that an exciton. So this is what an exciton is. It's this excited electron, okay, which can move around the material, but it has to drag along with it this kind of hole, this positively charged hole that it left behind. Okay, so you can really think of this as an electron moving around the material, kind of like with a ball and chain attached to it. So in analogy with hydrogen, we can talk about a stable size of this exciton. Okay, so like we have in a hydrogen atom, we have a positive nucleus and a single negative electron. So that's one positive particle, one negative particle. Okay, so it's very similar to the situation we have here. And we can talk about an exciton Bohr radius. So this is the radius at which this kind of size at which this exciton likes to exist at. It's very stable at this size. Okay, any smaller or any bigger, it's not very stable. And in semiconductors, this size is typically between 2 and 20 nanometers. So it depends on the material, but typically it's in that range. So it's really, really small. So the question is, we have this exciton that's generated in a semiconductor when we shine light on this material. And it has a characteristic size, it has a stable size. So what happens when we make the crystal smaller than that size? This is the crux of what a quantum dot is. Okay, so we shine some light on the semiconductor and we generate this exciton. And what happens when the crystal size is smaller than this Bohr radius of the exciton, this kind of natural size of the exciton? So we're going to think about this, you know, as physicists like to do. We're going to talk about a spring. We're going to model this Coulomb attraction, this kind of negative positive attraction by a spring that attaches these two particles. So if you watched Dr. Claire McElroy's talk on Monday, you will have seen she used this to model her polymers. So, you know, as physicists, we like to simplify things and use springs and balls and stuff. So we're going to model this exciton as two particles connected by a spring, and that spring has a relaxed length. Okay, so the spring has a length at which it naturally exists. You can compress it and stretch it, but when you let go, it will naturally go back to that length. Okay, we call that length A. And we put this spring inside a box that has sides that have length L. Okay, so what happens when we open the box? Well, it depends on the relative size of L and A. So we see here A is much smaller than L. So, you know, this exciton is in this crystal that has dimension L. And if we, you know, we can keep reducing L, you know, nothing really happens. If we imagine opening this box, right, nothing will happen, right? There's nothing will happen. We'll just open that box and that spring will just stay there. And likewise, even if we make L equal to A, so if we make the crystal the same size as this exciton, and we open that box, nothing necessarily will happen. However, if we make the size of the box smaller than this size of the exciton, this is forcing this exciton down into a smaller region than it wants to exist in. So when we open this box, you know what happens, right? This is a jack in the box. So when we open this box, that spring is going to want to go back to its equilibrium length, and it will kind of jump out of the box. So by forcing this spring into a box smaller than its natural length, we're kind of storing energy in that spring. And this is effectively what's going on with this quantum size effect. Okay, so it's a quantum size effect, but we can get an intuitive understanding without really talking about quantum mechanics at all. If you understand how a jack-in-the-box works, you can pretty much understand this quantum size effect. Okay, so as we change the size of the crystal, we can change the energy of this exciton. And that means when this exciton is kind of released in the form of a photon of light, that energy of the emitted photon depends on the size of the box or the size of the crystal. So if we look again at this material that I'm particularly interested in, copper indium sulfide, if you see on the diagram here, these horizontal parallel lines, these represent the bands. Okay, so this line at -4, this represents this conduction band edge, and the line between -5 and -6 represents this valence band edge. Okay, don't worry why they're minus, that's just a convention, that doesn't really mean anything. And we have this band gap, okay, this EG subscript infinity. This infinity means bulk. Okay, so these lines, they would go off, if we extended this graph all the way to infinity to the right, these lines would stay parallel. They're like train tracks. Okay, and the bulk band gap of copper indium sulfide is around 1.5 electron volts. Again, electron volts are just a unit of energy. And this Bohr radius, this kind of size of this exciton in this material, is around 4 nanometers. So you see the blue lines that I've just added, this represents the band edges of the quantum dot. So you see above 4 electron volts, these band gap, these kind of band energies are the same as in bulk. But as soon as we go below this Bohr radius, we're squeezing this exciton into a volume smaller than it likes to occupy, and therefore it has more energy. So we see, I've shown here the energy gap of a quantum dot that is 2 nanometers radius. It's slightly larger than the energy gap of a bulk crystal. Right? And if we go down to 1 nanometer radius, we see the conduction band is at -2 and the valence band is at -6. So that corresponds to a band gap of 4 electron volts. Okay, so that's UV light. Right? So on the right here, we have very large crystals, a band gap of 1.5 electron volts, which is dark red color. And if we shrink the crystal down to around 1 nanometer radius, the band gap goes to 4 electron volts. That's a very big difference. Okay, so the band gap of a semiconductor increases when the crystal radius is made smaller than the Bohr radius of the exciton. So for copper indium sulfide, hypothetically, we can span the whole visible spectrum just by changing the size of the nanocrystal from 5 nanometers down to 1 nanometers. Okay, so that's not a big change in size, but we can span the whole visible spectrum, hypothetically. Okay, so now let's talk a little bit about how we can make quantum dots. So there's 2 options to making nanomaterials. One is to take a top-down approach. So we start with big stuff and break it up, say mechanically, into smaller pieces. This is not a particularly good method. It's very difficult to control, quite expensive. So we want an alternative, and that alternative is called bottom-up. So as the name suggests, this is going in the opposite direction. So we start with fundamental building blocks and synthesize or grow nanocrystals. Okay, so let's look at some kind of cartoon-like images. So we start with our fundamental building blocks, so kind of atoms. Again, I'm ignoring any chemistry here. These would really come in the form of molecules or salts, but we're just going to look at them as atoms. Okay, we put them in solution, and if we heat up that solution and keep adding our atoms, we can obtain what we call a supersaturated solution. So this is basically a solution of these atoms that is extremely concentrated. And if we keep ramping up the temperature, eventually these individual components will form chemical bonds, and this saves energy. It's energetically favorable for them to form bonds and form kind of dimers and then trimers. And eventually, if we keep adding material and increasing the temperature, they can actually form spontaneously clusters. Okay, we call this nucleation. They form these crystal clusters spontaneously, and this saves energy. So these atoms are all kind of tightly held together. They're bonded very strongly, and this saves energy that scales with the volume. So that scales with minus r cubed. But we also form, when we form these crystals, we form a interface between the newly formed crystal solid and the liquid, the solution. And because of the surface tension, this costs energy. Okay, so this is an energy cost. So that scales with the surface area, which goes with r squared, where r is the radius. Okay, so before I show you this picture, I'll just say, we can, if we had more time, we could derive a critical radius above which these clusters, these crystals, are stable. So there'll be a critical radius which we could actually find. If you watch Martin Greenall's talk on Tuesday, you could use those same techniques to find a critical radius below which these crystals spontaneously dissolve back into solution very quickly, but above which they can stay in this crystalline form. Okay, so this is a photograph of me making some copper indium sulfide quantum dots, and you see the color change as these crystals grow. Okay, so down in this top left image A, they're probably around 2 nanometers, and up to the image in the bottom right, labeled D, they're probably above 5 nanometers. Okay, so we can span much of this visible spectrum just by growing the crystals, making the crystals bigger. Okay, so this ties back into what I was saying before about this critical radius. The critical radius for the copper indium sulfide is around 2 nanometers. Okay, so actually, even though hypothetically we could span the whole visible spectrum with this material, and because it's actually not possible to make crystals below, say, 2 nanometers for this particular material, we don't tend to see anything below yellow. Okay, so we can't actually span the whole spectrum. So one final thing I want to say before we move on to talk about applications is that as we reduce the size of a crystal, so we make the radius smaller, then the surface area relative to the volume becomes much smaller. So I mainly included this slide for the joke and the title. I don't know if anyone will get that. It's a politics reference. But if we follow this red line, at the right-hand side, okay, with quite big particles, 50 nanometers, the volume is much, much more significant than the surface. But if we follow this red line down as we reduce the radius, okay, we see that below 10 nanometers, it explodes. And what this means is that the surface area becomes much more important as we reduce the radius. So that will become important in a moment. Okay, so once we claim to have made crystals, how do we actually tell if we have? Well, we use a technique called electron microscopy, which is very similar to light microscopy, but instead of using light as our kind of medium, we use electrons, and we look at how electrons interact with a material, and we can very cleverly kind of form an image from those interactions. So you see here this white bar in the bottom left there, that's 5 nanometers. So you can see these are very, very small, and I've kind of zoomed in on this square in the middle there, just so you can see really that these are very crystalline. So you can actually see the atomic structure of these tiny little crystals. And from this, we can verify what the material is by measuring the spacing between these kind of lines that you can see. We can verify which material this is likely to be. And I said earlier about copper indium sulfide being interesting because you can play around with the kind of copper and indium. We did some very, very high quality imaging, and we saw that, on the left column there in blue shows you where the copper is, and the middle column in pink shows you where the indium is. And we see where there's indium, there's not copper. And where there is copper, there is less indium. Okay, so there's some very interesting kind of separation going on in these materials, which have very interesting effects. So this is still an active area of research. Okay, so finally, we've got maybe 5 minutes or so left. Let's talk a little bit about the applications. So the main reason we're interested in these materials for technological reasons, is the tunability. Okay, so the fact that we can control the size, right? control the color just by controlling the size is very useful. So thinking back to the stained glass windows where we had to, we'd use different chemical compounds to achieve different colored glass. Here we can choose a material that has properties that we like for other reasons and change its color by changing the size of the crystal, okay, keeping all those other properties that we've chosen the material for. So rather than the color requirements dictating which material we have to use, the color requirement is achievable with many different materials. Okay, so talking about these applications to do with the emission of light, well, it's the tunability mainly, but also because they're so small, okay, we can do some fancy processing, right? So we can have very flexible screens. Okay, so the quantum dots are being used in TV screens that are very thin and have the potential to be very flexible. And also the colors are much more vibrant. So this photo doesn't show that very well, but the color quality is much better. Biological imaging, we can label cells with quantum dots, so they're small enough to go inside cells. So we can kind of do imaging of biological systems using these quantum dots as labels. And their absorption properties are also very good. So they absorb light very, very strongly. And because of this tunability, we can match our kind of absorption spectrum to the solar spectrum, like perfectly. And again, we can do solution processing, like continuous, what we call reel-to-reel manufacturing processes that are much, much cheaper. Okay, so although the efficiency of quantum dot solar cells are maybe 10, 15, 20%, which is much lower than the record for solid state kind of bulk photovoltaics, they're much cheaper and more cost effective to set up. So although they're, the efficiency is lower, they're much more economically viable. Okay, and then finally, just to say why, many of these applications are achievable with bulk or indeed with molecular dyes. And the reason quantum dots in some cases are much better than dyes, for example, in bioimaging, is because of this large surface area. So we can attach all sorts of biological molecules that can be used to target specific cells. So, for example, we can put certain antibodies on the surface of these particles, these quantum dots, and that would mean that only, for example, cancerous cells would take them in and healthy cells would not allow them to cross the barrier. So we have this platform for bioconjugation, which allows us to do some really clever stuff. So here are some references. I'll leave them on the screen just for a moment so that you can pause and go back and look at them. And here's some contact details. So thank you very much, and we have some time left for questions. I shall stop sharing my screen.
Thank you very much, Matt, for a fascinating talk.
You're welcome.
I'll just remind public that questions can be placed using two channels directly in the live chat of YouTube, or if you would like to do it completely anonymously, you can type them in Padlet link, which is provided in the live chat as well. And while talk was going, some questions, in fact, arrived in the Padlet, and I will read them to Matt as I see them. So I see there is a question: how slow do these crystals grow?
Good question. So it takes a few hours. So you could, I always joke with my students that you could make these in your kitchen at home if you really wanted to. It doesn't take long at all. You don't need fancy equipment. This solution-based synthesis method is extremely easy, and it can be done by students. So I've had, before COVID, this would be a project I would typically give to third-year students or fourth-year students, would be to synthesize these materials in the lab and characterize them using various techniques. So actually the photo I showed you at the beginning, the picture of the copper indium sulfide quantum dots that looked red when we had the periodic table in the background, those were actually made by a third-year student. So yes, it's very easy to make, and it takes a few hours.
So in fact, you already answered another question, which was in Padlet: can students experiment with quantum dots? So yeah, the question is yes.
Yeah, so the first time I ran these projects, I would get students to actually make them. But really, there is a bit, like I explained it very roughly using thermodynamic arguments, kind of. I ignored the chemistry, and there is a lot of chemistry involved. So the surface chemistry, the molecules you include in the reaction actually dictate the size and shape of the crystals as well. So it's not just thermodynamics, it's reaction kinetics which are important. So nowadays I would maybe put less emphasis on the synthesis, and the students would look at the physical properties of this material. Yeah.
Thank you. There is here quite deep physics question just arrived in a Padlet. How does energy transfer from photons to electrons?
So there's something you should look into called Fermi's golden rule, I think. That's a general answer to that kind of question. That's a bit too much of a technical question to answer in such a format as this. But if you look, I don't know who asked that question, but if you look on our school website,
it's completely anonymous here in Padlet.
Okay. That's the Padlet one. So if you look on the school website, you can find my email address. It's mbooth@lincoln.ac.uk. Feel free to email me, and I can give you a much more rigorous answer than I could do here.
Thank you. And I see there are comments arriving in live chat from Sorsha. What a great project, lead me to my PhD.
Yes, so Sorsha was one of my project students. She was looking at coating. So when you make these quantum dots, they're quite often hydrophobic. So what that means is they're not soluble in water. So you can make them in oil, but if you want to transfer them to water, in order to put them in the body, for example, or to do some processing with them, then you have to do some post-synthesis steps. And what Sorsha was looking at was coating these hydrophobic crystals with polymers that would allow them to be stable in water. And yes, indeed, she went on to do a PhD. She's at Liverpool University now, doing some similar work.
Thank you, Matt. I see another question in Padlet, which is, which semiconductors are better for quantum dots?
Okay, so that depends on the application. So, so there's many considerations here. One is the reason, one thing I would say is that, and it's part of the reason I was interested in copper indium sulfide, is that many of the most widely used materials are the ones that contain cadmium and lead, which are toxic. So, they're not very good for big biological applications. So it depends on the application. It depends on which wavelengths, which region of wavelengths you want to achieve. So, for example, if you wanted blue light, you wouldn't use the copper indium sulfide for the reasons I kind of went through. So it depends on the color you need and other kind of properties. So you might want ones with high thermal conductivity, for example, or low toxicity. So it really does depend.
Thank you. And just watching two channels. There is a quite general question, which in fact somebody is asking every our speaker. What made you interested in this field?
I just heard the name of them and thought they sounded cool. No, actually, it's a funny story. So it's very lucky, actually. So I was looking for a PhD in quantum technologies, and one of my lecturers approached me and said, "Do you want to do a PhD in this, looking at quantum dots?" And to be honest, I hadn't actually heard of them before. I didn't know what they were. I had to go away and look into what they actually were. And they sounded quite interesting. I like the fact that they're very kind of, you can really look at the theory, and the theory behind all this size effect. There's still some debate in the literature as to what's really behind it. So the model I presented is the most widely accepted and presented. But there are people who claim that that's not really a good enough explanation. So there's open theoretical questions, but it also involves chemistry in order to make them. They're very, as I've kind of pointed out, there's many different applications. So there's just, there's lots of different components of this field that, there's lots of stuff to keep you interested, basically. Yeah.
Thank you. And I see there is a question in a live chat from Reese. Would you say this is the next big step to be commonplace in a phone screens, etc.?
Yeah, so the fact that you've got these, so rather than using bulk materials to make screens that are very kind of rigid, you can use these really, really tiny crystals to create your screen. And what this means is you can get this flexible effect, right? So this kind of idea of wearable technology is very, very feasible using such nanomaterials. So one of the references I put at the end there, if you go back and pause and find the reference about Samsung, they're the leading technology here in this quantum dot displays. And if I remember correctly, that article is about how they're looking to just kind of really focus on this. But there are other companies who are a bit more reluctant and claim that it will never really become mainstream. So there's differing opinions there.
Thank you. And now I see there's a question in Padlet about a bit of history. That scientist of the past, did he come any close to real explanation of color of glass?
So I presume this is referring to de Lavalle.
Yeah, I think so, yeah.
I don't know, to be honest. I have not read all of that book. I think you can buy it, actually. I was looking the other day, and you can actually buy the book. But he won the Copley Medal, right, for this work?
Yeah. What I remember, he won what was Nobel Prize in those years, a Copley Medal from Royal Society. Yes.
Yeah. So I know he was recognised by the scientific community, or in those days probably the community of natural philosophers, with this Copley Medal for his work in this area. So yeah, I expect he did a pretty good job, at least for his time. Yeah, I haven't. I'll be honest. I've not read the full book. It's not a paper. It's a book.
Yeah, and also probably, as we all know, style of writing changed so much in these 200 years. So it's very different. But it's also nice that close to Lincoln there is so much history, also history of physics and natural philosophy. It's just I'm looking. I kind of normally try not to ask my own questions, but I was really intrigued with that paper you put there. Is it one of the first papers on quantum dots?
Yeah, I think it's Ekimov and Onoshenko. They're credited with the discovery.
Right. Yeah.
I think they were hypothesized before by a person called Brew. So that equation. The slide where I was showing the band gap of copper indium sulfide, that equation at the top there, that's called the Brew equation, BRUS. So I think they were hypothesized before, but they are credited with the actual first realization.
This experimental realization, yes. I just kind of also noticed that apparently original was published in Russian and in English only translated 1 year later. So I wonder, it took a bit of time for this knowledge to come.
Yeah, well, that's quite common. I think during that time, the Iron Curtain and all that. But 1 year is not that long, actually.
No, it's but
later, that's quite good.
But it's nice. Right, I think we approach into good time to close. I'm just checking if there is any last question. Oh yeah, there is just arrived one question. Just a second. Can the color of quantum dots be altered electrically?
So you can. I'm not quite sure what you mean there. So if you apply electric current to the quantum dot,
probably, yeah, that's what
that can excite these electrons from this valence band up to this conduction band, so that they can conduct electricity, but it wouldn't really have a big effect on the size of that band gap. I know. So these crystals, they actually have an organic layer of molecules on the surface. I won't spend too long here. And depending on the dielectric properties of this organic layer, it can change the band gap very slightly. But we're talking like 1%. So it's a very small effect. But yes, there are many, many things that can affect this band gap. And they all contribute different changes. Yeah.
Right. Okay. Thank you, Matt. Again, I see we are really good on time and managed to answer all the questions. So I would like to thank our speaker, Matt Booth, and also everyone who came to listen. Also, some of our alumni. So pleasant to see you in not face to face, but through the live chat of YouTube. So the modern technology helps us to stay connected. So thank you again, everyone. We hope to see you during our next talks. We still have 3 more talks in our Lincoln Math and Physics Week. And in fact, next one will be just in 3 minutes in mathematics. Thank you very much for listening. Bye.
Thank you, Andre.